Problem 15.3, take 2. So we have 0.1 moles of sodium hydroxide added to 1 liter from 15.2, and the same thing added to water. First need to calculate the pH before we get the pH change. So in 15.2 we have 0.5 molar, I believe it's acetic acid, and 0.5 molar sodium acetate. I'm going to use HA and A- just so this problem can be used multiple times. So, before we do anything, we have to actually think of the chemical reaction and do some stoichiometry. We're talking about moles here, so we calculate the number of moles of our acetic acid, as well as our moles of our conjugate base, multiplying our volume times our concentration. Now what you'll notice is this is a reaction as a one-sided arrow. It's not in equilibrium because this is acid plus base. So instead of an ice table, it's some stoichiometry. We have before, after, and change. Initially, we have 0.5 moles, adding 0.01, and we have 0.5 moles because of our given. Now, this is essentially a limiting reagent problem. Our hydroxide is a limiting reagent. We're going to subtract from this side. We've got to add here. So our after concentrations, 0.49 moles, 0.51 moles. Now for future reference, this is in 1 liter of solution, so our moles is the same thing as our concentrations. We notice that it changed slightly. We want to calculate the pH. Henderson-Hasselbalch equation is our best bet, because we can take the pH plus pK plus the log of the conjugate base over the acid. Substitute in, solve, one shot. Right? Put in our Ka, put in our A- from here, 0.51, HA, 0.49, we get 4.76. If you like to do the Ka way, that'll get you there too. Ka is 1.8 times 10 to the negative fifth over our products, reactants. Substitute those in. We solve, we get 1.73 times 10 to the negative fifth for x, and our pH of 4.76. They're the same answer. In part B, we're adding this to water. Sodium hydroxide is a strong base, so the moles is equal to the concentration. If we take the negative log of that, that gives us the POH. We want the pH, so we subtract from 14. Now, ultimately, this question asks for the change, right? We want the change in pH. The original from that equation was 4.74. That was from the previous example. So to get the change in pH, we take 4.76, our final, minus our initial, and we get 0.02. Wow, that's small. If we look at our change in pH, if we add water, our new pH is 12. Now water is neutral, so that'd be 7. Our change is 5. Wow, look at this. This is small. This is not small. The purpose of a buffer is to resist change in pH, so that's what this problem proves. That when we have a buffer, and we add a strong base to it, the pH only changes a little bit. When you compare it to water, it changes a lot.